Hello, everybody. My name is Kevin Kotchik. I'm the founder CEO of Chemical Q Device, here for event seminar 129. This is Thursday, April 4th, 2024, for how to recode LLMs layer by layer with tensor network substitution. So if you don't know, large language models or LLMs, they're oftentimes associated with generative AI. They don't have to be, but that's the trend, like ChatGPT, that type of stuff. Now, this is an example of this Bloom 176 billion parameter model. And it's just one of those cases. If it has multi-layer perceptrons, self-attention layers like transformers is the keyword. So transformers kind of is taking over on the neural net side, and it's being used quite extensively, especially for generative AI. So what I'm going to go over here is basically a lot of the MPS stuff. So most papers that you see today are going to be matrix product state. So it's a type of tensor network that are composed of tensors. And this is also referred to as tensor trains. So you'll see it as literature as tensor-trains or TT, and then for matrix product state, MPS, they both mean the same thing. There's a specific type of tensor network that has very good algorithms. It's in one-dimensional, so it's basically you have to get the data down into one-dimensional where you're still getting good performance, and at that time, you're taking advantage of the best algorithms right now. And we're talking high dimensions, so high dimensional data, that type of stuff. Now, the thing that you'll see in recent literature is compression. And there was actually some studies on this that have been built using, say, GPTs and certain types of tensor network compressions. It's this formula on the right. So instead of D to the N, or like number of entries, now it's N times D times X squared. So it's a lot more favorable mathematically, as you can see. So if you get up to 3, so D to the 3 or D to the 4th, it grows. This is an exponential equation where the ones on the right, I think, are just constant. And then this is quadratic with the X squared. So that's the efficiency benefit. And then the more challenging part is trying to match it up with the performance. And this has been, kind of increased ever since image classifications and into current day, studies that you see. And I'm going to go over a little bit of background with this. So this is basically the LLMs and transformers. So as I said before, like the majority of them are using, some type of transformer in it. And actually ChatGPT stands for generative pre-trained transformer. So this could be used for weight reduction, physics prior, more explainable neural nets. That's kind of like the given. And then the harder part is to go through and prove it, like with some type of SHAP values or line values, those types of things. And I'll go through also layer by layer how this looks for existing large language models. So you see Terra Quantum with GPT too small. I was able to get on to GPT-2, small, medium, large, and XL through Hugging Face this week as well. So I'll talk a little bit about coding too when we get to that section. And also with Llama, 7 billion parameters. If you get up to above 7 billion, I think that's kind of the threshold as far as like the happiness between the networks communicating, cloud computing, the amount of RAM, for GPUs. And I had one of these that was like 8 by 7 billion parameters, and it was taking forever to load. Okay, so here's the first example here. So the main thing here is you have the matrix on the left, and it goes through tensor train decomposition, for all of these subsequent steps. So when you see this USV, I've covered this in previous weeks. This is singular value decomposition. This is a core 2 matrix product states, and it basically you're removing less relevant information as the dimensions get smaller, by contracting this this middle S term there. So that's just what you'll see. And again, don't get too confused by literature. When you click through these links, I'll have it put up. When you see tensor train decomposition, it's the same thing as matrix product states. However, when it says used on deep multi-layer perceptrons, this is like deep learning, fully connected neural nets, that type of stuff. So it's using tensor networks where it makes sense to get things compressed, run faster, more explainable, those types of things as well. Okay, so this next one is a really interesting diagram. So if you've ever studied transformers, you could take several, seminars on this, or you can actually go onto literature and then figure this out as well. So the one on the left is this local spatial multi-head attention, and attention mechanisms are the core of transformers. It's basically how they behave. And the one on the right is this global spatial multi-head attention one. And it's tensorizing those. So another term you'll see it tensorized. And, obviously my background's been in quantum inspired, but a lot of these papers, they won't mention, much with that. It's just, this is a specific way of processing. It's very efficient, and if they're at that point of publishing, then it's usually they've been able to get the accuracy or loss or some other metrics in combination with the efficiency of like a matrix product state. So you see these tensorized feed-forward networks, these are quite common in transformers. And on this specific one, they have specific applications. This is traffic flow forecasting. But basically, these big neural nets, they'll be out there. Like I can have access to GPT-2, like I said, the 4 variants of that. But say the 3.5 that everybody can access, for free, that's not an open model on Hugging Face. And it works a lot better than I would say the GPT-2. However, you can modify, you can retrain the GPT-2, you can, on new data, you can basically fine tune it, for a more compact model that would run faster for your specific reasons. But it gives you a good appreciation, because I got into the code a lot of it this week as far as like how good, the GPTs are now. I tried GPT-4 a little bit. But basically, they're not explainable at all. And the thought behind it is to get a lot of these tensor networks benefits of explainability, compression, and, of course, you're going to have less parameters. And this has already been done, and I'll get to those papers there too. So for this next part, you'll hear this autoregressive matrix product state in this specific one. And anytime you hear unsupervised learning, this is like generative AI. This is, ChatGPT. It's basically if you have image, or, more commonly you have like a text and you want additional text generated onto that sentence that's unsupervised. The software is creating or generating this new solution. It's not based on anything that's been labeled previously by humans. It just has a ton of data that it's seen before. And so basically with AMPS here, is it's still using matrix product states. And then you see that it's a specific type. It says it combines MPS from quantum many-body physics and autoregressive modeling, which is very synonymous with neural networks. And actually GPT, like the OpenAI software, and I believe others too, use some form of autoregressive neural networks in their products today. I think it's not like as big of a feature as say like the other transformers. So you see, here's a good example, and I think this specific one has been built upon. Now this is a very important paper, and it's in the figure here. It says authors, and it's calling this autoregressive neural network tensor network, a hybrid in the middle. And you're probably familiar with these, more of the fully connected neural networks in the middle. So say, for instance, this middle layer is going to have a lot of parameters because it's connected to other ones too. But a lot of times it's the middle layer that's just associated with a lot of the neurons and the next layer, and then the ones previous. And that's how you get a lot of parameters and big model size. So that's not always fully understood. And that's what tensor networks are helping with, is basically, a lot of times you can get better orders of magnitude, better loss. I got with a controllability study that I did. And, again, I think the biggest thing will be the explainability, because no matter how far and how fast and how powerful these get, in your responses, if you use them for medical diagnosis, I think at some point, you just can't say, well, it was better than the human response, or if we ran it 10,000 times on average, the whatever LLM is creating a better answer on average. So, that's the promise with a lot of, or this is the hope with tensor networks, is to improve that. So on this specific one, you see the matrix product state, and then it's basically going in at this specific point. Now, the significance of this paper, and obviously the names are big too, so NSF, MIT, and Harvard, is that it was able to get a highly expressive And then also the matrix product state gives it a physics prior, which is kind of like pre-training a model, which means you're bringing in some previous knowledge as opposed to starting from scratch. And you know just how hard that is. So a lot of times you go to pre-train based on somebody else's parameters based on that data set. And now you have your specific data set. It's a lot smaller. And then, in this case, you're starting off with some quantum mechanical information, i.e. a physics prior, and then that's a starting point for the model as well. It's technically quantum inspired. So that's what they call this, the output here is, or the model, this new one, and it performed better than, the single models with traditional neural networks on the left or tensor networks on the right. And, the whole goal with this specific one was a conditional wave function tensor for each site. And they say it was fully working. So that was the challenging thing. So in the years past, you get efficiency, but always trying to get that performance. And, like fully functional models was more challenging. But they say, great opportunities for generative modeling, so this has strong kind of like LLM implications with this specific paper. And then this next one is basically multi-way multimodal transformer. So you'll see the linear tensor generation function. And at this point, you're going to see a lot of the similarities, MPS, tensor network, i.e. tensor train, and used in however you can to get the advantages of quantum inspired tensor networks for this specific one. Now this one also is very interesting. Now if you don't know Miles, it's Staudenmeier, so it's spelled like this, S-T-O-U, and he runs iTensors with other people too, or it's technically iTensor, and then the coding version is called iTensors or iTensor networks. And I rewatched a couple of his videos this week, and this is his graphic at the top, and this one's called an infinite MPS, this top diagram here. And then the bottom one is basically this mu MPS enabled sequence level parallelism that the paper used. So everything on the bottom is relating to that paper. And so this specific talk that Miles gave on the top, he definitely recommended that. And he recommends, he mostly focused on like quantum circuit kind of stuff, but it's such a broad field for, not just machine learning, but generative AI. And a lot of people are using tensor networks, in very productive ways, I would say. Now, this next one is kind of interesting as well. So again, MPS or tensor train, and it has, so this is what's going on the left, with the tensor network. And here's the smaller model in the middle called tiny. And here's the bigger model on the right called large. So you can see here, so another MPS, and, it can be more effective than vanilla RNNs, which is like, just the standard ones. And they were able to conclude some relationships between this TTLM and second order recurrent neural networks as well. So very exciting stuff. Now, this next one is they say in specific explainable natural language processing with matrix product states. And you'll see basically the first one, a graphical representation of the mapping between a single layer racks for sentiment analysis, which is binary classification, is something that is said, is this a positive statement or is it a negative statement? That was the task in the paper. And then this B represents the tensor network, so dual MPS. And then the C represents the tensor of rank 3, okay? So, and I'll get into this some more, and as far as like the directions of as this one kind of winds up here too, is basically, they say the last equality is compactly represented by the standard tensor network graphical notation as shown in the figure, and then whose building block is the tensor A, from this first part. Okay, so all of this, these two next to are basically the large language models that are generative AI. And when OpenAI first started to create GPTs, they've gotten better over the generations. And like I said, this one, GPT is too small. I believe this is the one I was working with as well. And I typically got a little bit better. Like say, for instance, I was able to do sentiment analysis, which is that, is this positive or negative? I also did a summarization. So you give it a line of text and it'll kind of summarize more on that. And then I did text to text generation. So I left a sentence kind of hanging, and then I'll try to finish it like this generative unsupervised way that it doesn't have the computer's figured it out on its own as we program the software to behave. Okay, so what's going on here is basically on the left is this Terra Quantum, their compressed GPT-2. So it's taking GPT-2 and then, or the small, and it's basically tensorizing it, okay? So they address this through embedding, multi-head attention, feed-fold network. I've also found some other papers that the specific tensor network is this Kronecker decompositions. I've found some more on those. So, so you should be able to Google Scholar through a lot of this stuff if this is your prime occupation. But just keep in mind that some people just won't mention quantum inspired. Other people, it's just more traditional. So if you just had a more traditional coding background with LLMs and generative AI. And then on the right, here's the standard model. So that every time you see this cross, there's a tensor network associated with it. So that's what happens: tensorizing, embedding layer, multi-head attention, and feed forward. And the results seem to be, pretty similar. And even if you can't, on the next paper, it seems to be, getting the very best performance. But if you could prove explainability through this, is like, every single layer, say these are more kind of orderly systems in general, or they're able to be explained better, then it kind of addresses what's in the news, this year especially, is we're going to be so high in compute and performance that others will redefine explainability as just running it tens of thousands of times and then just analyzing the output for it. So it'll probably be a mix of both, right? Because I've had people on this discussion and they say, well, we just go with it. We just go with whatever is the answers produced because they trust it. And on average, I think even more than just on average, you're getting, to these better solutions a lot faster, using unsupervised generative AI without, any human labels. And this next one is kind of like the big one. So this is the Multiverse paper et al. And this is an example. So Llama, 7 billion parameters. And by the way, Hugging Face has, all the smaller chat GPTs, Llama, Grok, there's just a lot of models up there. And if you caught one of the previous posts that I did, is basically they have a thing called pipelines. So you can just do really fast inference, basically switch whatever's in the quotes for the models. And then you're going on to, the next cell, you could switch to a different model. And it's very rapid, very fast. And it seems to, work pretty well, especially for 7 billion parameters. The OpenAI ones are a little bit faster. So what's going on here is basically, this is going to have a transformer and this self-attention that kind of like flags it as being transformer, multi-layer perceptron, which has been created, many years ago. And this is what they tensorize here. Now, they used a matrix product operator, and I've used this in another demo too, and it seems to work quite well. So I would tend to, if people say they want to get crazy with tensor networks, I say, hold on, really focus on the lightweight ones like MPOs, because no matter what you're trying to do, it's going to have some complexity to it, or a time complexity. So anyways, they had good results with this, got a funding deal after this paper and the weeks after. So how does this all look like? So basically, this is actually from a different type of neural network. But the theory is the same: is you can create the class of MPS, and then you're using MPS, and the code was longer than this specific block, while you're using Hugging Face or while you're using whatever's. Now, I think with other services like iTensor, which is Julia based, they tend to be on the more cutting edge of things, like probably less lines of code, from the sounds of it, especially easier to use, configurable, and also for bigger systems too. But nevertheless, you could do this, and as you can see, I think this is just torch.nn, which is the plain old torch, to create this matrix product state with the code right here. And basically where all of this is going, the vast majority of the literatures are matrix product states or tensor trains. Like I said, sometimes you can get it. The key is getting to this one-dimensional tensor network while still keeping your accuracy, right? So it has to be done in a very specific way, I would say currently, in order to do that. And there have been a number of papers that have been able to take advantage of the MPS or tensor trains. Now, many will report performance and explainability benefits, but like I said, there's other ones like tree tensor networks. There's other MERA, there's PEPs. So PEPs can be 2D, so they get into these, more intricate. So it's just a tensor is like the dot in the MPS, and that whole thing is basically the tensor network. So when they say MPS tensor network, it'll have those dots that I showed you before. Each of those dots or the circle are tensors, hence the name tensor networks. And so basically, I described this before, so you can use PyTorch to do that. I don't think that, well, it just depends on what you're doing. So say you create your class of MPS, and now you can use that, in very specific parts of the other LLM. And Hugging Face is basically well incorporated with PyTorch, a lot better than TensorFlow is what it looks like. And you need to use PyTorch and Hugging Face. I don't think Hugging Face works on its own. So Hugging Face is the repository for a lot of these large language models that are associated with computer vision, and a lot of those are generative tasks. And then you also have NLP tasks. So this could be natural language processing. So it's like text to text or text to something. Okay, so the other way is basically Julia-based iTensor. And, after watching numerous number of their videos, I'm still really excited for this, but I want to get in, I want to get, I'm kind of close to, the Terra Quantums and the multiverses as far as what they've done in substituting layers for an existing Python-based, right? So that's where I'm at. I'm not quite over. I've done some Julia-based programming, but minimal. But that's what they say is it's, for more complex systems, greater performance. But like I said, if you start off doing tensor networks, you'll want to catch a bunch of Miles Stoudemires. He works at Flatiron Institute, and again, he's one of the he leads the iTensor. So Flatiron Institute is a subdivision of Simons Institute, which is based in the Bay Area, and then Flatiron is on the East Coast. So in one of these, they said they created an MPS solver. So it's basically so you don't have to start from scratch every time. So no matter what problem you have, it's sounding like it's a lot easier to use. So this one sounds like it's ready. So as of say June, of last year, this solver for MPS is usable. Now the other ones, TTNs and PEPs, which have been harder to get that performance. Sometimes the algorithms just aren't as favorable as MPS. That these have been under construction, but nevertheless, don't count on iTensor even though it's Julia based. It's just if you want to do very specific things in other areas of physics, I would definitely check that out as well. So the other thing, and they said that there's a lot of good stuff coming up with iTensor using Julia, and there's a Julia conference coming up this summer. So a sequence of recent tensor network papers support broader tensor network use in medical generative AI. So I mentioned that one NSF MIT paper with Harvard as well. Kind of like this was the first one that they get all the working parts to work between the tensor network. They got the physics prior, which is basically you're starting with some quantum mechanical, thing that's inspired by quantum, and then you're still getting the expressivity of auto regression, neural networks. And the other one is, language modeling and explainable natural language processing studies have also utilized MPS as well. So I think this is a really good place in the technical thing that kind of backs up some of these, say 4 or 5 weeks of seminars too. Now, explainability in my mind, because it keeps popping up. And if it's the kind of thing like we have a thing in town, it's just an old town, and it's where, the original foundations of the town had started. And it's kind of like, who would ever think of having an automatic, knitting machine for your clothes? And, still to some people with ChatGPT and say generative images. It might not set with them well as far as the computer's doing all of this now. But I think over the course of the time is people will get really used to it, and not only used to it, but reliant on it. And, if you see from other people that, this is the era that we're in as far as like it's the human AI team, or it's basically you have to work well with AI. That's where that's at. So basically, we'll finish up the slide and we'll switch over to questions too. And so I showed you the Terra Quantum, the multiverse computing, and I think the next step is taking the explainability studies even further. I think this is a huge issue, right? But it just depends how society reacts and how much we trust unsupervised learning. Now, Stanford AI, HAI, which is human AI, they say substantiating, explaining, and assessing claims with reliable scientific sources are needed. So that's why it's always good to back up your sources. If you ask, I think it's 3.5 for GTP. If you ask for sources, I don't think it can give it to you. I saw a demonstration where that did happen, and one of them kind of got, because these are very well connected neural networks. There's a lot going on as far as trying to stop at a specific layer and get an explanation. So I'll leave you with this quote here. So it says and this is the Stanford University human-centered artificial intelligence. So many commentators have declared the end of healthcare as we know it, given the apparent ability of LLMs to pass US medical licensing exams. And then here's from before, but healthcare practice involves more than being able to answer a multiple choice test. It involves substantiating, explaining, and assessing claims with reliable scientific sources. And on that score, Gen AI still has a long way to go. I don't see any humans being replaced, in the current years. But it will come down to, I'd say, in the next few years, of the people that use AI, like chatbots, they will have an advantage over people that don't. And you just have to get used to talking to a computer, through text prompts, just like you would with other people. So, and it's good to do all different types of research with this. I wouldn't just lean on one, right? Because, yes, you'll gain a lot of information using ChatGPT, but you also need to go to events or at least online ones, and talk to people. Awesome. So I saw hand raised. Go ahead.
Yeah, so I have a question. So I know that of course this is for tensor networks, but I wanted to ask, are there any other models for like explainability, especially in like large language models and like machine learning?
Yeah. So there's Bayesian. I think where all this left off with these like the traditional machine learning ones is that they are really good explainability, just like tensor networks, but they tend not to be able to get the state-of-the-art performance. And another one of my colleagues, I brought this up last weekend, they said that basically there's kind of a stopping point with a lot of those other, very explainable machine learning techniques, and then it's to continue some other your study somewhere else. So yeah, there are some, but of the ones that I've seen and I've read these reviews, that seems to be the case. Is it's kind of like tensor networks has a lot more to offer as far as the order of you have an existing system that you have to stick to, and you're trying to work your way down to an NPS. Like you start from there, and then you kind of just to a more efficient system. But yeah, that's my understanding with it, is that they've been developed before. You can get explainability, but they're kind of lacking on performance, where tensor network seems to have the advantage.
Yeah, so I also wanted to extend that question to more. So I know machine learning in general has emergent phenomena. Are there any like models to capture that, or is it just explaining the model's thinking and then trying to extrapolate the emergent behavior, or are we sort of doing another model where we can also predict based on the parameters what emergent phenomena might arise from it?
Well, I think that we're already at that stage of having emergent phenomenon. And, it's kind of amazing to, instead of Googling, a certain subject and then getting, 4 or 5 sites to click through and kind of go through different paragraphs and that type of stuff. So, I mean, if you have something more specific.
Yeah, so I wanted to ask, is there like a model, or is there like a specific way or technique to predict emergent phenomena, or is it just trying to go off the things that we have from like Tensor or like Bayesian? So the question is there like what is it? Is there research on emergent phenomena, trying to predict it, or are we just going off of the,
And are you kind of talking like general artificial
yeah,
intelligence?
yeah.
Yeah, I mean, in that case, I think that's still some years out. I think the Jensen Huang, said NVIDIA. There was the big GTC conference, I think, last week, and he had talked about these things, and he had a different quote from a different kind of conference. He said within 5 years, expect to be significant replacement of coders, human programmers, from these fundamental levels. And say for instance, in that specific one, he said, make sure to have this like a skill set in digital biology or farming or these types of things. But as far as general or singularity and these type of stuff that I hear other people talk and I talk to about, is that it seems like it's still off. Now, Jensen did say that the computers will speak, basically the language is human, and it will be able to do and process any different type of programming language that we know today. So that would be like Python and PyTorch and others, that it can do it all. And he said not to get a degree in computer science, because by the time you graduate and get done, the computers are going to be so far advanced with that. So, outside that, and if you get into like, does the computer have consciousness and can it just do everything on its own? There are things called agents. So that got brought up. NVIDIA calls them NIMS, NIMS, and they're basically software agents at this point, and they're talking to each other like humans would and completing human tasks like a worker would.
Yeah. All right. So I wanted to also ask, so are there any other behaviors that quantum machine learning sort of exhibits more than classical machine learning? Because I know in some cases, of course, we're using classical machine learning now, but are there any other interesting behaviors QML exhibits than ML?
Yeah, I mean, I'm sure you could do it, and this is kind of what Miles Stoudemire did, with this big tensor network paper at Flatiron, is he took the same exact circuit that was run on a quantum computer and just beat it with time and accuracy and speed and these types of things, and corresponding to an infinite number of qubits, meaning that not limited by the math. There's also dequantized algorithms. So dequantized algorithms. So there was a lot of work in the field of quantum machine learning, and the hope was to take these 8 different QML algorithms. Once the hardware came around, you could get exponential speed ups, and that whole field is basically they've dequantized at least 8 of these, to the point where it doesn't make much sense to run it on a future quantum computer. So in that regards, I think that you still could have the possibility of being faster than the machine learning algorithms, because they're closer to the quantum, like the algorithms that were thought to have exponential speedups. Yu and Tang had led that. I know that they're not as functional as the machine learning, like a traditional machine learning algorithm. They're mostly going after speed. So I say a lot of this is going up to tensor networks, because you're talking about high dimensional, low rank approximations, and then these algorithms are very well studied, and there's a lot of papers associated with them.
All right. So last thing I wanted to comment on. So I was looking at Penny Lane's they had expose on the quantum machine learning models, and they were testing it and benchmarking it against classical ML. And what they found out is that extremely mature machine learning models completely flat out beat QML in terms of pure performance. So I wanted to know, in your opinion, where do you think QML specifically sits, especially when, as we're coming to this point where quantum computing is becoming like serious, and like error correction is moving, where would QML truly beat like normal ML?
So the way she did that paper, I didn't read the whole thing, but I ran all 26 or 27. I think she ran like 15. So I classify a lot of that software as 1.0 software. It's not optimized for classical computers. They're optimized to run on some future, quantum hardware. So I don't think it's really, like I said, I would go in different directions than QML at this point, because of the dequantized algorithms. on the data side, you probably need to get quantum data, but I don't think quantum sensors are even producing quantum data. And, so I did a big write-up for this, and, I would head towards different directions.
Yeah, okay, that's fine. That's it.
Yeah, any other questions? Good to see. If there's any specific slides you have questions to, I can go back. Yeah, and it's good to see a number of people, that have come before are here again. And like I said, there's not much time because the AI will be really speeding up. And so we have a comment here. Yeah, so, and other people from other groups and that type of stuff. But if the technology like tensor networks has had a lot of development, and like I said, especially in 2024 coming around the corner with performance, then it's like the perfect timing that it's like AI is moving so fast, and it could probably slow down a little bit on the development side to incorporate tensor networks to get some of these explainability benefits, compression, and there's other ways of compressing LLMs as well. But kind of like to take advantage of the tensor network benefits that it's known to be good with. Awesome. And then so I think the good thing is just there's a ton of research that's been done, in this field, and it's looking really good. Because when you get to the point of say like, okay, they got this to this specific point, and then now we can, do it this specific way. Now we have this working model, that's both like an autoregressive neural network and a tensor network. And if they're saying use it for generative modeling, that type of stuff is very, it's encouraging. It's working, and a lot of times it's better. The people are getting better results across the board. Yeah, any other questions?
Hey, Kevin.
Yeah, go ahead, Ron.
So I see that you've been talking about tensor networks for a little while now. Unfortunately, haven't seen all of your presentations over the last month or so. Can you just give us a brief summary of what is meant by that term? And
Yeah.
is it more of a concept, a framework, an entity? What's going on with the term?
Yeah, so the main thing is you'll have some high dimensional data. So this could be like a patient that has, heart rate, temperature, and these types of things. Now, classical computers have a hard time. It's called the curse of dimensionality. They have a hard time looking at all these different variables all at the same time. So there already exists, principal component analysis, and I think partial least squares. And some of the math is similar to tensor networks, but tensor networks also brings in kind of like the structure behind it. It's not, it's not just, smaller things, but you can also do things with like PCA and PLS and those types of things. Now, ultimately, so if you have this, huge tensor, that's basically, if you try to run it on the biggest GPU, because of that initial math equation where it's like quadratic in time and resources, it's a d to the n. So d to the 1, d to the 2, this quickly, very quickly leads to a huge problem, the curse of dimensionality in GPUs and CPUs. So what tensor networks does, and there's a core principle or core mathematic approach, and I touched on it today, but I've covered it a lot more in previous exercises. It's called singular value decomposition. So you take an original matrix and you split it into 3, and say the first column and the first column has the high variance, or it's the most important data. The second column has less, and the third column, and so forth. So depending on how much you want to approximate this or compress it, if you wanted to compress it down to 0, you're going to lose all your accuracy. But if you keep removing columns of these matrices, then in a controlled approximation way, keeping the most important information and say like the first columns, then that's where the power comes in. And I think it's also that, like PCA uses this, partial least squares uses this approach as well. But like some of the, the quantum mechanics, the priors are coming in, into tensor networks, and it's, it's something like the mainstream doesn't really understand or work with, and it kind of gets, it can get complicated right away. So that's the biggest thing, so this has been used to disprove, many other types of it, hardware, and then especially keeps building on itself in a lot of these tasks, with papers this year.
Okay, so again, is this more of a concept and there's supportive frameworks, or is there some entity out there promoting this?
Yeah, it's a very simple concept. So tensor networks were conceived back in like condensed matter physics, and it's taken a while for them to become more mainstream, and it's taken them a while to know how to use them better, to keep the accuracy as close to 100%, and on top of that reach these big data problems and high dimensional data sets that you couldn't do without tensor networks. But the very best thing to do is go through a bunch of Miles videos. So for instance, in that case where you have a patient with all of these dimensions, or say like the heart rate and then the temperature, and if that gets over 5 or 6, and you try to run that tensor. So here's another way of looking at it. You have a scalar, which is, you can look at it like it's order one tensor, and then you have a vector, and then a matrix. And then these are all just a generalized category of tensors. Okay. So as you get higher and higher, with dimensions or order, then, you refer to it as like an order 4, order whatever. But the small ones are easy to run, like I said, with like scalars and vectors, or vectors are for GPUs. But it's a general term used for matrices, and you just say order whatever tensor for that matrix. And like, if you look at it, like it's just like a bunch of different dimensions on, all this medical inputs or whatever. And then they show you the tensor network, like the MPS, the corresponding of that. It's a controlled approximation of that data, right? So if it has 10 dimensions, it's going to reduce, it's called the rank, which you're losing some of this less vital information. And it's the same kind of techniques that are embraced with, like I said, principal component analysis and PLS. And it takes a while. It does, because you have to study this, and it'll just dawn on you like, oh, okay, now I see, these 10 dimensions, they can't be run efficiently. Like if you were to try to correlate all of this data, that's the curse of dimensionality for classical computers. So tensor networks, are for basically maintaining as much information as you can to get that, to receive, to get to the problem now you can solve with tensor networks. So it'll take some time, you'll have to definitely watch some, a bunch of seminars, and I've had to rewatch a couple of them.
So is there a kind of a new awakening of this, given the fact that a lot of the new GPUs that are coming online actually have tensor cores?
Well, they actually kind of go hand in hand. And
yeah,
by the way, if you check on Colab, there's like this monster 330 gigabyte TPU right now that it's just stalling on the first line for me. But no, like there's still like, it's like an exponential slowdown. Like if you go D to the 10 compared to D to the 11th, those types of things, no matter supercomputers, whatever, they just can't run it. So NVIDIA, they actually have gotten this up to, on the quantum side, up to, they said tens of thousands of qubits they've simulated using tensor networks. So, and, these things correspond with like, complex data, if you just have regular classical data too, they also correspond to these types of applications. So NVIDIA has kind of led a lot of the, through cuTensorNet. So I would definitely check that out, because they've done a bunch of studies, and the ones that I've seen were like, I want to say, 1600 and 800 or 900. So that would be like 1600 GPUs and 800 or 900, qubits. And in some of their other things, they have massive amounts of this. In tensor networks, that's what they're known for, is they're efficient. And then the hurdle is to get the performance after that. But they're definitely a leader in this field.
I guess it makes sense. They all of their new stuff is like the new cores. The new GPUs have different kinds of cores now, and they're talking about how many tensor cores they have in comparison to how many graphic cores, or actually they have administrative cores now.
Yeah.
So it's neat.
Go ahead.
Yeah, so I was just I mean, it seems like a tensor really is just a multidimensional matrix, right?
Yeah.
And it's just there's different ways of decomposing them to reduce complexity.
Yeah, and another way is basically starting off with some big tensor, and then you need to get it into these smaller chunks because those smaller chunks just run better. So if you have like, I don't know, 10 dimensions, and then it's now into 3, 3, and like 4, something like that.
So the trick is to decompose it into independent chunks.
Yeah,
so they're not dependent on each other. Yeah.
Yeah, and depending on the applications, that's the tricky part is to, because it's always going to be efficient as far as I know, and then, try to keep that performance or actually beat the performance of whatever, if it's accuracy. But it's very synonymous, especially like matrix product states and matrix product operators for compression, and they're very lightweight kind of, tools. So they themselves aren't contributing to, increasing the model size by much. So yeah, it's just like you have to look at it, a lot of it fundamentally. And there's there's some good notebooks up that MPS code that I shared. That one was and you could take a look at that too. That's you could run it on Colab kind of stuff.
Cool. Yeah, I absolutely see the benefit of being able to decompose a large dimensional object into smaller independent objects that have smaller dimensions. Obviously, it would all be easier to train and compute and all that good stuff.
Yeah, and
that's pretty cool.
Yeah, I mentioned this before, so it's the iTensor. In my opinion, just listening to Miles talk, and I think it's Matt Fishman. He gave some JuliaCon talks, which is like the Julia, big event, I think in the summer. And they kind of seem like they have the greatest grasp that I've seen as far as like, when they say that we have a solver for MPS, it sounded like it's a more universal thing. So as opposed to just reinventing the wheel every time you need to incorporate tensor network, in this case an MPS, into some other system, and the other ones are under construction, and that was last summer. And they said they keep having good stuff come out. I just I'm kind of just strapped for time a little bit, and I have to get so I just ran a bunch of these different LLMs off of Hugging Face, for different tasks, and then now I can start to create my own, and based on all that previous data I can compare things and rerun. But it's Python based, and that's Hugging Face is Python based, and they have like 350,000 different LLMs, or a lot of them are LLMs. So let's just say models.
Very cool. Thanks.
Yeah, and I guess, for everybody else coming from just different parts of machine learning, and I was mostly doing supervise, and these models are trained on a lot of data. And the core essence is basically, if you have a Hugging Face model, is that, you typically need to use PyTorch or TensorFlow, but that was trained on that data, okay? And then those parameters are set, and that's the pre-trained model. And then you're starting with that, and you can train on new different conditions and even changing epochs and, different hyperparameters and learning rates on your own data, probably smaller. And then now you have a new set, and then you can claim that it performs like this on this specific task, where say GPT-2 small performs like this. So yeah, it's very exciting stuff, because I struggled with this, say 3-4 weeks, and I was trying to just dissect single models, and I came across this called pipelines. So I'll put that in the chat. So Hugging Face pipelines, and it's very low code, very low number of lines of code. And you can build a lot of this up from a simple tutorial. They also, the GPT is still better than Hugging Face's Hugging Chat, for me at least, and it's faster too. But they can help you, if you want to do text to image generation. I did a bunch of hospital settings for that one. And then, like a smaller model would probably be like a sentiment analysis that loads quickly, and one that is generative by nature. So say if you're like, my friend was here, or my friend was at the blank, and you don't fill in the blank, you just leave it like quotes, and then it'll just generate some text. So the models towards the top of the leaderboard, or the more well-known models, tend to do better. But it's interesting because you take it for granted how well ChatGPT 3.5 works. It's free too. And I've had other people come on and they say, yeah, we just use this all day.
Yeah, I have access to GPT-4 Enterprise, and it is downright addicting. It's just crazy how good it is, but it still makes mistakes. It still hallucinates. It still can misinterpret your intention, but especially in the image generation stuff, it's pretty amazing.
Yeah, and if I were to create an analogy, and again, in town here, there's a couple that they just sew different garments, like on a weekend, and their son is actually a software engineer, which is more interesting too. But how is that transition when, like, machinery to make clothes, and then all of these other steps that we've had today? So I don't see any problem with unsupervised machine learning and these types of tasks fitting in at all. It's just, I think it'll go through some more checks and balances with explainability, and from all the literature, it looks like tensor networks can help with that. But it's like FDA calls it probable benefit over probable risk. And their last kind of October of last year, they said, they gave this big spiel about ChatGPT and LLMs, and they said, as of today, we have not yet approved an LLM generative AI LLM as an FDA approval. And some things don't need to be approved, right? They're not considered in direct, harm of a patient, those types of things. But we're going to see more stuff from that. And I think maybe the first kind of stuff that rolls out will be this administrative stuff to help people. If you get so many X calls, that it'll do like that'd be like a speech to text, or like a summarization of when people call in, using this generative AI type of stuff. But yeah, I think even drug discovery, even if it creates a new drug, you would still have time to test it. So I don't think it's that case. But if it's something like a final diagnosis, those types of things, probably not quite ready. And all these things, it depends on the data that it was trained on. So ChatGPT 4, or higher, however high you want to go, was trained primarily on the internet, which is like way too much data, that you would need for medical whatever. So another positive thing is that all these LLMs, and one of the previous commissioners, Scott Gottlieb, talks about these things, is that it'll be trained on medical specific data, using hopefully high performing models similar to what's today.
Yeah, that's happening right now. Google has their MedML stuff. I don't believe that's available to the public yet. NVIDIA has a massive set of pre-trained medical stacks. Demonstrations of that show quite convincingly, like it could be an assistant, like during a patient encounter, where it can ask questions of it, and you can. I mean, I saw one demo where you could actually ask it coding questions. It's not making the diagnosis, but it's providing information. The provider is still the final person in charge, but asking a question like, did this encounter have all the bullet points to meet a level 5 office visit? And it answers those questions. questions
Yeah.
like that. It's pretty amazing.
Yeah, and again, like I don't think humans, like anybody, can just interact with next gen software in the future. I would highly recommend to learn how to do machine learning if you haven't done it, to be actively engaged in doing it, and to also use some of these tools now, like the Chat GPT. I haven't tried Copilot. I know Google at least has Copilot. And that type of stuff is that you need to be understanding how computers work. Like a lot of times you can't feed all the data in at one time, and that's called a batch size. And if you don't know how many batches you would need of that batch size to make an epoch, well, you have to know these fundamental things. You can't just ask a computer, make me the best performing, text to image model, for this specific thing in medical, and you don't know what a loss is, like loss functions and gradients, those types of things, because you could further specify, I need a lower loss, and then it might, train for more epochs, and a lot of these things will be even more modernized things. I think, I don't know how much of the original terms that will keep, like learning rates, epochs, these types of things, but I believe that you'll have a huge leg up, and this ties in with what they're saying. It's like, those that know how to use AI will keep your job in the future. That's not just using Chat GPT all day. That's, coding on your own, developing models, reflecting on them, making them better. In my opinion, I really think that you'll have to have a strong technical background to interact with future software, AI.
Yeah, it's amazing where it's going to go. I mean, I see that everybody's got co-pilots, not just Google, for coding, and the direction that's heading is right now. It's somewhat tedious. You have to trigger it somehow, but eventually, instead of the co-pilot, there'll just be a coding buddy that just sits there and just as if you were pair programming under an agile environment, except instead of another person, it's this AI entity who watches what you do, converses with you, might trigger you to do something as opposed to you always triggering it. They say that there are ways away from that, but that's where it's headed.
And a lot of the sentiments I get, and these are just clips of like Jensen talking or OpenAI quotes, because the OpenAI had said, the person that uses ChatGPT in the future, as opposed to your other coworker that doesn't, you'll have an advantage. These things, and again, I still think, like, if you don't have a huge technical background, you're not going to have that basic, or not even know how computer works and software works, and all of a sudden come up with this awesome solution to something, and being able to talk to other people about what it just did, those types of things. So one of my other colleagues on Sundays, he says that, for sure, doctorates and PhDs and, especially the very technical people will still be in demand, but maybe like the more kind of like some might say like mundane or like the basic tasks, it's like an expert software engineer say like, oh, I just need this for this. And it'll just code it in like 2 seconds.
Yeah, I mean, humans still outstrip all of the technology in terms of sensory perception, so that's going to be difficult. But I see it more as like a provider inside of an encounter would have like a virtual consult, just kind of like sitting there in the wings that can, instead of them triggering it to ask questions, the consult could just chime in.
Yeah. And that's kind of what they said too, is, it's all software agents at this point, as far as interacting with other computer programs, and they kind of can do similar types of electronic tasks. And, for robots and stuff like that, it'd take longer.
Yeah. Cool stuff coming.
Yeah. Any other questions? And, just keep it to the news, I would say. And, like I said, I do a Saturday advanced ML and then a Sunday ML. And I don't really think that you could just roll out of bed 5 years from now and just anybody, like that's the sentiment that I'm getting. Anybody could create this awesome website. Yes, a website. But another thing that was shared by a colleague of mine is they said a lot of data is private. so you can't train on data that's not accessible, right? And the core essence of the success of a lot of these programs is the open internet, and whatever people put online, as long as it's not password protected, it's just normal, whatever. And I don't even know how much it can look at LinkedIn or, for sure, I think Twitter. I found a Facebook model where it does train on Facebook data, and that specific model, probably needed to, or was an earlier version. Let's just put it like that. So it's a very interesting situation, and it's definitely, people will have different tasks and jobs, but some of my friends, before I moved out west, they don't know anything about computers. And I said, if you have these human interaction jobs, and they said a salesperson is a top, will be continue to be a top job for humans to have, because most people don't want to talk to robots, in person or online. They want to talk to a rep. Awesome. Any other kind of last questions or comments? And I appreciate everybody coming on. This has been Event Seminar 129, Thursday, April 4th, 2024, for how to recode LLMs layer by layer with tensor network substitutions. Thanks everybody for coming on. Have a good night and have a productive rest of the week. Take care, everybody.